Okay, hello guys and welcome back. We'll still talk about operators, but now we actually start coding. The last video was only an introductory video. This one will be pretty short. I'll talk about the different types of operators. Well, not really different types of operators, but we'll get to it, don't you worry. Okay, so let's start with the arithmetic operators. So this should be pretty easy for you, right? So let's say we declare an integer result addition, for example, and notice that I use a camel case. You should get into the habit of using camel case as well, because it's convention, and do a simple addition of like 1 plus 2. Of course, we can always print this out. Yeah. No surprises there. 3. Obviously, you can also do this with subtraction. 1 minus 2, you obviously get a negative number. Okay, and now maybe let's talk about multiplication. Result multiplication. And you can see how we are actually starting to combine things, okay? We are doing a variable declaration, and we're saying, whatever, this is a little box, and we put inside the box the outcome of this operation, okay? This is how you can metaphorically think about this stuff. Let's say 2 times 3, so we symbolize the multiplication by this asterisk operator. Let's print it out. Of course, this is, I know this is not too exciting, but you'll have to learn the basics to get started. Let's say, and remember what I told you, if we are doing divisions, we should always use like a floating point data type, but that's a fractional data type. And we should use the double, as I told you in like the first video of the series, the first real video. So let's say result division, let's say 3. You can also tell the compiler that this is not an integer, because you may remember the problem we ran into last time by simply writing it in this notation with a decimal point and like this 1 decimal place. Of course, we can also print this out. 1.5. That's obviously true. And yeah, of course, there is also, there are different operators. So maybe let's talk about the modulo operator, because this is actually something new you can learn. It's also an arithmetic operator. So let's say, and you can actually, modulo operator always returns an integer. So yeah, I'll talk about the modulo operator in just a second. Let's say modulo, a result modulo division, or whatever you call it. Let's say 5 modulo 3. There you can see this funny syntax with the percent sign. Maybe you can ask yourself, what do you think is what is the expected outcome here? Run it. It's 2. Why is it 2? Because in the end, what the modulo operator does, and it's actually pretty easy, it asks how many times does this 3 fit into that 5? So obviously 1, and what's the rest? So it's what's the remainder? So it's asking for the remainder of the division, 5 divided by 3. Okay. And 5 obviously simply is 3 times 1 plus 2. Okay, so this little 2 is a remainder. I don't know how to pronounce it actually. So this, so it outputs 2. Should be pretty obvious. Once again, I'm talking about how stuff should be obvious. I'm sorry. So asks for remainder of a division operation, and there you can see this will always be an integer, right? It's not possible to double. So the result of such an operation. Of course, there's also the power operation, for example, taking 2 to the power of 3 or something. But I won't talk about that yet, because it's not important, and you actually have to use a library to do that in Java. At least I think so. Now let's talk about the what I call the arithmetic logical operators. So we remember the output is a Boolean, so we have to declare a corresponding data type if we want to store the outcome of that operation in a Boolean. Of course, this makes no real pragmatic sense, but bear with me. Boolean is smaller, for example. Yeah, 2 is 2 smaller than 3. It obviously is. We can print it out. You see, the output is a true value, so this is obviously true. And if we flip it, it's obviously false. Yeah. This is the strict is smaller, right? Because it's well, let's give this a better name. Is smaller or equal, for example. We could write 3. Okay. Pretty easy. You know these operators, right? And I won't repeat it for the, because this is just too dry for the bigger than or equal operator. It's simply the same, but let's print this one out. You see, I go really quickly here because it's just a little bit dry. Yeah. Okay. Let's talk about the logical operators. So let's define maybe Boolean true value, true. Boolean false value, false. And now we repeat a little bit what I already told you in the previous video, right? And this is just for demonstrating purposes. As soon as you'll be able to do more exciting stuff, you won't do stuff like this. But this is simply, in a sense, combining of what we already learned. So we're declaring a variable, a little box of data type Boolean, and we store the result of this operation in that little box. So it's just tying nicely together with what we already know. So we can now print out true value. And remember, this is just to show you the syntax, and. So we represent the logical and in this way. And false value. Maybe you can pause the video. What is the outcome? What's the expected outcome here? Obviously it's false, right? But if we have like two true values, of course we could actually do this. True and true, it's the same. This should output true, but as soon as I input false here, it's then false. We symbolize the OR simply by doing this. Okay, by this little symbol right here. So what is the expected outcome here? It's true. Okay, maybe let's stop printing this out. Once again, this is how you comment stuff in Java. I already told you. So maybe let's think about the negation. No, this is dry, excuse me, but you have to get through it. So remember, the negation is the syntax is this little exclamation mark, and we can negate a true value, for example. The outcome is simply the true value flipped, so false. Yeah. And I think this covers everything we talked about previously. But now let's demonstrate what I called operator overloading. So importing topic, and you don't have to know this name, but you have to be familiar with the concept of operator overloading. And this simply means let's define a string. Let's call the string hello. Simply holds the string hello. Define another string world. And now let's concatenate these strings. Maybe store it in another variable as well. Hello world. Hello plus world. And then we print it out. We run it, and you see the product is a simple string concatenation. If you want to display it more nice, you can like make an empty space right here. And we'll talk about string formatting in detail in further lessons. I think on the intermediate learning level then. And you see this operation here obviously works way different than just what we wrote here. So that should be pretty obvious. And then let's talk about class of operators. I didn't talk about, at least with this name. They are the bitwise operators. They are very close to the Boolean logical operators, and I think they are logical operators or binary operations on the binary numbers represented in binaries. Let me give you an example. Let's declare an integer with a value of, let's say, 12. Yeah, and the output, and let's think about 12 in decimal is in binary. Okay, we should be familiar, but maybe because you may be new to this binary system, let's think about it again. So this simply means 1 times 2 to the power of 3 plus 1 times 2 to the power of 2 plus 0 times 2 to the power of 1 plus 0 times 2 to the power of 0. Okay. This evaluates to the power of 3 is 8. This evaluates to 4. This obviously evaluates to 0. This evaluates to 0. Sorry, I forgot to comment there. Okay, let's maybe organize our thoughts a little bit more neatly. Okay, then we simply add up, and in the end we get 12. So this is why the number 12 is represented like this in the binary system. Let's define another little variable with the name with the value of 5. Sorry for all my mispronunciations. We won't get over this process of converting decimal numbers into binary numbers for now. Just believe me, or even better, think about yourself. Right, this is the correct representation of the number 5. Yes. And now we can do interesting stuff with these bitwise operators. I didn't talk about them in the last video because they are not that important, especially not on the beginner learning level. And I really questioned myself whether I should discuss them in this video. But I think for the sake of a complete introduction to, not complete of course, but almost complete introduction to operators, you should know them. So let's store the result in an integer. Okay. And you'll have to stick with me for now, because if you want to understand why we store it in an integer, let's say result bitwise and, okay, this is why we call it a bitwise operator, but this will become more clear as we progress, A and B. Okay, notice how this syntactically mirrors the logical AND we talked about earlier, but this is an operation on Boolean values, false or true values. This is an operation actually on bits, and this is why we call it a bitwise operation. So let's think about this stuff a little bit. So as I told you, so this simply means 2 logical AND 5. Bitwise AND, I'm sorry. So 2 is represented, 12, I'm sorry, is represented as 1100. 5 is represented as 0, 1, 0, 1. And now think about what I told you. Of course, this in the sense can also be interpreted as truth values, right? So in the end, what we learned in the case of logical operator simply translates. So this is simply 0. This is also 0, because let's imagine 0 and 1 is symbolizing truth or falsehood, right? And this is bitwise AND pronunciation with on the AND. So something false and something true results in something false. So this is just what we talked about when we talked about the logical conjunction, when we talk about the logical AND. This is always also evaluates to 0. This evaluates to 1, and this evaluates to 0 again. So in the end, if we translate this back into like a number in the decimal system, okay, this is 4, okay, in decimal, obviously. And if we print out the result of this bitwise AND, let's have a look at it. A system out print line bitwise AND. The result is 4. Okay, and you can maybe watch my last video where I talked about the truth table definition of these logical operators. Okay, simply realize the input, okay, for this operator is of a different data type than for this operator right here, because this operator takes as input truth values, booleans, and this operator takes in numbers in a binary representation. But in the end, it is very similar to a logical operator in the true sense of the word, because it with every bit of that binary representation, it performs these simple logical operations. So, okay, A is represented binary as this, 5 is represented binary as this binary string, and for every bit, we can perform the logical operations we talked about previously. The result, okay, there's also a difference between the logical OR and this bitwise, the logical AND and this bitwise AND, because the output is not a truth value, it's obviously a number as an integer, okay? So, as you can probably already guess, you won't, these are very, you might ask yourself, why are we doing this? This seems a little bit abstract and weird. We are doing this because this is a very efficient way of computing numbers, okay? So, if you work in game development, for example, you could do this to actually boost performance. I won't demonstrate like all of these operators, I'll just give you the syntax for now, and this is a good homework for you to actually think about the stuff and think about the expected outcome. But by giving you this example should be pretty obvious. Maybe write it down in the comments what every one of these operations I'll demonstrate now, or what the expected outcome should be. Okay, let's say, how did I call this? I called it int result bitwise AND. Okay, let's copy it. Int result bitwise OR is simply A or B. So this follows the same rule. We have the logical OR, okay, which is symbolized by these two lines. And we have the bitwise OR, which is symbolized by simply one line. So it's actually easy to remember. Then we have something, the exclusive OR, I didn't talk about earlier, but maybe it's actually a good homework for you to figure out how the exclusive OR should work, okay? Maybe I'll give you the truth table, and from there you can figure it out on your own. Result bitwise OR is A, and that case, which that symbol we usually use to indicate explanation. So it's maybe a little bit weird to you. So let's define the truth table for the result of the bitwise OR, and then you should actually ask yourself, what is the respected outcome? XOR for exclusive OR. Okay, and the truth table simply is, let's say these are our two, let's think about them as booleans, because I'm talking about the truth table. So 0, 0, 1, 1, 0, 1, 1, 0. Yeah. And A, XOR B. And remember, XOR simply means exclusive OR. Okay, should write it like this maybe. Exclusive OR. And the truth table is zero, 0, 1, 1. Okay? So, sorry for the long pause. I thought I heard someone knocking again. I'm getting really paranoid here. So this is the truth table of the exclusive OR, and meaning so either A or B is true, but not both of them, and not neither of them. Okay, so this is what an exclusive OR is, and now you can think about how the bitwise exclusive OR should work. And now, maybe as a last step, let's talk about bit shifting a little bit, because this is also a bitwise operator, but let's call it bit shifting. Okay, let's say you should take a number int num, let's say 2, for example, to make it really clear. Okay, or maybe not 2, maybe let's say 5. Yeah, let's think about the binary representation again. So this is simply sorry, I got really lost for a second. 0, 1, 0, 1, I think. Okay. So this evaluates to 1, 2, 4 exactly. I'm correct on that one. So this is a 4-bit representation, of course, only. And now let's say we shift every bit to the 2 to the left, for example. And for this, we simply write end result bit shift is equal to num2. Okay, let's print out the output and think about why this makes sense. Out print line result bit shift. Okay, let's delete it. Let's run it. It's 20. Okay. Why do you think it's 20? First of all, let's think about the binary representation of 20. And this simply is 0, 1, 0, 1, 0, 0. Okay, so 1, 2, 4 plus 16. Okay, so you see everything got shifted 2 to the left and places, and you can, yeah, just this whole binary string, so to speak, got shifted to the left by introducing 2 0 bits at the right. Of course, you can shift it in another way. Result bit shift left, I should call it maybe. Of course, you can also shift it in the other way. In the other direction, I mean, result bit shift right. And this simply is num2. Okay, you can ask yourself what should be, what is the expected outcome here? I'll give you 1 second to think about it. It's 1. Because if we just truncate those, right? It's just 1. Okay. As I said, if you don't want to bother with these bit shifting operations, I can understand. If you're not into like really performance boosting, they're not, you won't encounter them that often, but I wanted to talk about them just for the sake of completion, right? Maybe one last word on other operators, okay? And I hesitate calling them operators, but in a way they are. Think about the black box model I gave you, right? And they are what I call the incrementing operators. So, for example, let's declare all decrementing operators. First, let's say integer some number is equal to 3, and then we can simply write some num plus plus. Okay, and this is a simple shorthand for simply writing some num equals to 3 some num plus 1. Okay, this is just a useful shorthand you encounter often, especially when looping, when we talk about looping. But you can see this is not really an operator in the sense we talked about earlier, because this is, of course, you can model this as an operator in a way, but it's also reassigning a value. It's also, we also use an assignment operator right here. So yeah, but this is in the end also just semantics, so who actually cares, right? So we can print it out, and you see, so the value of some num changed to 4. Let's stop printing this annoying hello world. Where am I printing this annoying hello world? Yeah, you can also do this and decrement it. System out print line some num, so it should be 3 again, right? And tada, it is 3 again. So in the sense we talked about, they are not real operators, but they are operators like in a more abstract sense. Of course, you can use this black box model in even more abstract sense of saying, okay, I know what the input is. Okay, the input is some variable of type int or double. And then there is some sort of operation, and in the output, what I get is the var plus 1. Okay, but in that way, this metaphor stops this black box abstraction. It just simply isn't working. So I just wanted to talk about these operators, so you should be familiar with them because we use them a lot when actually looping, when actually writing for loops. Okay, so I think that's all there is to it, and I promise you, like this video on data types and variables and operations, it's the most dry topic in my whole course. So in the next chapters we'll talk about control flow, okay, and then when we start talking about looping, we'll actually be able to write some really nice programs, and then we will actually start coding some projects. But I'll have to get you off the ground somewhere, right? And this is what I'm trying to do here. So let me think again if there's something I forgot. Of course, I could go on and on and on, right? But I think this is the gist of it, and I think you probably got it, especially when you already watched my introduction. So see ya in the next video. Bye bye.